people have to come. Only about 200 are there, 225. Let's give them 1 minute extra until
Okay,
everybody
let's get started at 1:31.
Yeah. Did you save Q&A somewhere?
Yeah, I can see Q&A here.
Did you save them for posterity? Will it be? Because once we log off for Zoom, they will vanish, isn't it?
Yeah, that's right. But our TAs are documenting all the Q&As, answered, unanswered in a Google Doc, and we will share all the questions and Q&A at the end of the day.
Okay.
So we are not losing those questions.
Okay.
Probably we will lose the question on chat, but definitely we will keep those in Q&A.
And maybe before your talk, you should tell the participants that questions should be asked only in Q&A, not in chat.
That'll be helpful. Probably I will mention that.
Yeah. Chat is for technical issues.
Okay, I think that's a good way to distinguish. So this is 1:31, and this is time for learning inference, basically statistical inference. Before we get started, let me announce two things.
Did you start recording? Oh, okay. I see that.
Yeah, I started. Yeah. So two things. One is about the asking questions. I have seen 90 questions in Q&A part. Let's use Q&A for lecture-related questions and the chat box for some technical issues that you need to tell panelists. Second, I just made a final edit like 30 minutes ago. So please refresh the PDF if you're downloading and trying to write something on the PDF offline. Okay, just wanted to mention that I made the final change 30 minutes ago, and it will not be changed anymore. It'll be fixed. Okay, let's get started. This lecture is about statistical inference. Due to the time limit, we divided the entire lecture into two parts, inference 1 and 2. But basically, this is about statistical inference. I said the main theme of this lecture, 2 hours and 20 minutes. The main theme of this lecture is about likelihood function. So this is all about likelihood function. Simply likelihood. So in a semester-long inference class, I typically talk about inference of the whole semester. So the difference between this 2 hour, 20-minute lecture and a semester-long lecture is that there are not many examples. I typically put the fundamental example, but it's not as various examples as possible that you might have seen in some semester-long inference class. So that's all about this lecture. Everything is about likelihood. So at the end of the day, if you get some clear idea about likelihood function, then I might be very happy about that. My job, I mean, well done. You are okay. You earned all the things that I intended for this lecture. So one more time. So the emphasis of this 2 hour, 20-minute lecture will be about likelihood function. So if I start talking about likelihood function, please pay attention to that. I will also mention that. So first, what is statistics and why we need to learn statistics? So statistics is a data-driven information science that does two things: extracting its useful information from the observed data and quantify uncertainty of any quantity of interest in a principled manner. And it has become pretty popular since we started hearing famous terms like big data, data science, machine learning, etc. It has become quite popular because people try to extract useful information from the big data, a pile of data. I mean, like the survey, like the Rubin Observatory LSST data. Probably it will be pretty challenging to extract useful information from such petabyte data, but we are trying to learn some principle about extracting information from the data. So for that purpose, let me introduce some terminology in statistical inference. So population, by the way, in this setting, let's say we are interested in some proportion of the Earth-like exoplanets orbiting stars within 10 parsecs of the sun. So the population in statistical inference means the entire group of objects that we are trying to make an inference. So in this case, it will be all the Earth-like exoplanets orbiting. So in this case, all exoplanets orbiting blah 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 blah. So sample is a fraction of the population that we actually collect, where we actually collect the data. So we can think of this as those observed by telescope.
Like Kepler data.
Yes. I mean, there are so many exoplanets detected or undetected, but the sample here will be a small fraction of the entire population. So it can be the data, it can be the exoplanets that we actually detected from the telescope. Small portion of the entire population. And statistic is a numerical summary of the data. So it can be kind of, if we have some n observations, like 100,000 of object we have in the data, then it'll be a numerical summary of the property of those 100,000 objects. For example, it'll be a sample mean, sample variance, median, maximum, median, etc. So statistic is a numerical summary of the data. For your reference, as David mentioned in probability class, by tradition, we typically use capital letters X to denote the data that we haven't not yet observed. And we typically use small letters to indicate the crystallized value, the realized value of the random variable. So by random sampling n objects, small n objects out of the population of size capital N, the random variables, the n random variables will be realized into n specific numbers. So let's say, for example, xi, the ith random variable, is defined as 1 if the ith exoplanet is Earth-like, and it will be 0 otherwise. So I'm defining a binary indicator, which takes on value 1 if it is our interest, if an event of interest happens, and it will be 0 otherwise. If we define all the random variables for the data we have observed, then we can think of a numerical summary. For example, sample mean, which is the sum of all the small n indicators, and we divide it by n. So this will be sample proportion of the Earth-like exoplanets in the sample. Parameter is an unknown quantity that indexes the probability distribution. For example, it can be the mean mu and variance sigma square in the Gaussian distribution, because mean and variance completely determines the Gaussian distribution. And in statistical inference, in many cases, population characteristics of interest are typically modeled by parameter. For example, let's say if these indicators, follow some Bernoulli distribution. Bernoulli distribution specified a random variable to have binary values, depending on whether the event of interest happens or not. So in this case, theta, which governs the probability of an indicator being 1, is the population proportion of the Earth-like exoplanets. Is the population proportion of the Earth-like exoplanets. Sorry. So what I'm saying here is that what we actually want to know is the population property, the actual proportion of the Earth-like exoplanets out of all the exoplanets orbiting stars within 10% of the sun. But that quantity of interest can be a parameter of a distribution, probability distribution. And this is called a statistical model. I will explain more. Here is one interesting discussion about parameter. So let's say another example. Is theta the parameter? Sometimes this is a vector of all the unknown parameters. An unknown constant I typically use const dot to indicate constant, or a random variable. Typically, we call frequencies. We call frequencies who believe that theta is an unknown constant, but fixed constant, but just unknown. So for those people who believe that theta is just an unknown constant, we call them frequencies. And we call the people who believe that theta is a random variable, we call them Bayesian. So the philosophical difference between frequencies and Bayesian is that how they think of the parameter. How they actually think of probability in philosophy. Is theta an unknown parameter, unknown constant, but just fixed? Or is it a random variable, which has some distribution? So you can think of all parametric distributions into two biggest schools, like frequencies and Bayesian. But what I want to say here is that their intersection, this football-like region, football region, is all about likelihood. So all frequencies inference will contain some aspect of likelihood function, and all Bayesian inference is also based on some likelihood function principle, because Bayesian is basically using likelihood function, and they add some prior information of a parameter, which is theta here. So this emphasizes my theme one more time. So the theme of this lecture will be all about a likelihood function. And if we learn likelihood function very well, we can use the frequencies tools very well. And at the same time, we have good fundamental background about the Bayesian inference as well. So the emphasis will be likelihood function. Since we have a separate Bayesian class taught by Tom Loletto, who is a great and wonderful Bayesian in the field of astronomy. And my lecture will be focusing on frequentist approach. We will approach the likely function from frequentist point of view. So from now on, theta is an unknown constant. It's not a random variable that may have some distribution. Okay, S matter. Typically denoted by theta hat. Sometimes people use capital X as well. A statistic is a function of data that is used to infer some specific parameter. So for example, sample mean, sample proportion that I introduced before. Sample mean is used to infer the population proportion. So sample mean here is an estimator for theta, we call it. Estimator for theta in this case. And estimate, which is a little bit different from estimator, but in a simple manner, we can say estimate is a realized value of estimator, because estimator is a function of random variable. It is a random variable, so its value will be randomly realized depending on the probability distribution it has. So estimate, we typically denote it by theta hat and small x to emphasize that this is a calculated value from the data. So here, the realized value of the sample proportion will be here, small letter sample x bar. Sometimes we distinguish these two cases, estimator, estimate. Estimator of a function of unrealized data and estimate a function of realized data. But in many cases, those two are clear in the context. So typically we don't write down this capital X or small x, and we just use theta hat like this. And let me tell you about some relationship between probability and statistical inference before we get into the likely function. Probability and statistical inference are two sides of the same coin. So in probability, we are interested in quantifying the uncertainty of obtaining the data given the model and the parameter values. For example, a typical question in probability class is that, if the data are from a population distribution which is Gaussian with specific mean like 17 and specific variance, for example, 1, then what is the probability that the sample mean, a summary of the data, standard deviation from the true population mean, in this case 17? That is a specific question in probability, and statistical inference is the opposite. This time, we're not quantifying the uncertainty of data. The data are given in the statistical inference. Given the data, what are the most likely values of the parameters in the model that we assume? So those are the two aspects about the relationship between probability and statistical inference. But let me focus more on the direction for the statistical inference, from the data to model parameter, because this is statistical inference class. Okay, then why do we need probability in statistical inference? Let me talk about that. So in probability, we have learned several families of probability distribution. For example, Bernoulli distribution, binomial distribution, Poisson distribution, Gaussian normal distribution, gamma, beta, etc. In this lecture note, I only talk about 4 distributions: Bernoulli, Poisson, normal, and exponential distribution. But the reason we learn these distributions from probability class is that these distributions are building blocks to make a statistical model that is basically a set of assumptions about probability distributions of the data to account for the randomness of the data and data generation process. Here is an example about that process. Let's say we are interested in measuring some brightness of some galaxies, and the brightness of galaxy I out of n galaxies is measured by a certain telescope, and we assume that, which is the start of the statistical model, that it is measured around the unknown true brightness with a Gaussian measurement error. And we can express this statistical model as xi, which is the measured brightness. Let me use some different color. Measured brightness is equal to the unknown true brightness plus some random noise centered at 0, meaning that the measured brightness will be plus minus of the unknown true brightness. This is what we are assuming. And epsilon I also follows some Gaussian distribution centered at 0 with some unknown, some variability sigma square. So this is a model, but sometimes it'll be easier to just express the same model in a simplified form. Like the measured brightness is just a realization of a Gaussian distribution centered at the unknown true value mu I. Let me. So here is a Gaussian distribution centered at mu I. Then a realization of the brightness, the measured brightness, will be realized around this mu value, but most likely near the mu I, because that's where the most probability density is concentrating on. So it'll be very less likely to be realized in the tail area. For example, there are possibly many xi values, and the random realization of those measured values will be governed by the statistical distribution, in this case, Gaussian. So the question is this statistical model the true data generation process? I'm 100% sure that this is not. This is not the model our gods used to give us the measure value. I'm sure this is absolutely not the true data generation process. Then why do we set up a statistical model? The reason is that if we set up a statistical model that governs some randomness of the realization of data, then we can understand the uncertainty involved in the brightness measurement in the data. So I think David and Tom also talk about this phrase, but I repeat the phrase, quotation one more time here. All models are wrong, but some are useful. I'm sure every model is wrong, but some may be very useful to improve our knowledge about the random process, random experiment, random data generation process, which is told by George Box. Okay, this is about probability for building a model. Like until here, it'll be probability for building a model. And then we are focusing on the specific 3 topics of statistical inference. It's not infinity, it's inference, my acronym. I'm sorry about that if it is confusing. So in statistical inference, our interest is whether what the most likely values of the parameters in this model, given that we have n observations of the brightness. For example, in this model, the unknown parameters are from mu1 to mu(n), and there is another parameter sigma square that governs the spread of the Gaussian distribution. So if we have n observation, n measurements, what will be the most likely values of these parameters? That's a key question in statistical inference. And there are three topics regarding that types of inference. One is point estimation, interval, the other is interval estimation, and the last one is hypothesis testing. So we will go through these three topics from now on. Before that, let me answer some questions before I move on. Just for curiosity, what is the part that left over in F region? So likely, that's a good question. So you can think of how to quantify the uncertainty using the likely function. If you use likely function to make a parameter, then there are so many ways to extract some useful information about the uncertainty, for example. So, not all frequentist methods are likelihood function based. There are empirical likelihood and some other types of likelihood function. There are many, basically. I think that's a question. That's the answer to this question. Eugene Kang and Aaron Weinstein. Happens quite often in modeling and science. Presumptions to make things manageable. Is that different from saying knowing? Oh, this is from the previous probability class, I think. And Eric is still writing an answer to this question. So let me answer that question if Eric doesn't finish after this course. Okay, so let me move on. So point estimation. So here the question is, what is good estimator for the unknown quantity theta, which is a parameter in a probability distribution? And I told you that typically the quantity of interest in a population is typically modeled by the parameter in the distribution. Okay, to answer this question, what is good estimator? We need to define the definition of goodness. What is good in this context? And if we define that criteria, then we can say which one is best. So this topic is all about those things. We first define the criteria to judge the goodness of estimators, and we try to find a way to get the best estimator for any parameter of interest. Okay, throughout, in terms of notation, I'm going to use small x without any subscript to indicate a vector of observed data. There will be n, the observed data of n objects, for example, and theta without any subscript will indicate a vector for all of the unknown parameters, which is typically quantified by p, small p. Small p will indicate the number of unknown parameters. For example, if we assume that the data are coming from a Gaussian population, definitely the number of unknown parameters is 2, because in a Gaussian distribution there is mu and sigma square unknown quantities that governs the distribution. In our previous example here, the number of parameters p will be n plus 1, because there will be n mu's. Each center for each data, each datum, and one more parameter that governs the spread of the distribution sigma square. Okay, that's the number of parameters. And point estimate basically is the same as estimator, the definition of estimator and estimate. One thing I want to mention is that point estimator, by adding the word point in front of estimator, I'm typically meaning that this is basically single number summary. Basically the same as the definition of estimator. A single number summary, I meant. Summary of the data. So it can be sample mean, sample median, minimum, maximum, standard deviation, variance, etc. I also typically use RVS, which to indicate the random variables. variables. This is acronym basically. Random variables. So point estimator, which is a function of unrealized data and n of them. So it'll be theta hat. We typically omit the notation capital X because sometimes it is clear whether it is realized or unrealized. And let's talk about the criteria. Three criteria to evaluate point estimators. So how good is this estimate? What makes an estimate good? Basically, these two questions are related to the final question. Can we say anything about the closeness of an estimate to an unknown parameter? So we will talk about several criteria to measure the closeness of an estimate to the true parameter. Because we want our estimate as close as possible to the unknown true parameter, right? So all the criteria here are for measuring the closeness, closeness. Unbiasedness. As I mentioned briefly in the beginning, an estimator is a random variable because this is a function of unrealized data. So this is a random variable, meaning that it must have a probability distribution. So let's say here are two distributions of estimators. So this one, distribution of theta hat 1. And the other one is distribution of theta 2 hat. Basically, the unbiasedness is about whether the center of the distribution of the estimator is the same as the unknown true parameter or not. So in this case, in the first case, distribution of theta 1 hat is unbiased case because the center of that distribution is the same as theta. And the distribution of theta hat 2, the second estimator, is basically biased because the center of the distribution is not aligned to theta. It's far from the theta. And we typically call the bias the distance between the unknown parameter theta and the center for the distribution as a bias. In this case, it will be biased about the second estimator. So that's the definition of bias. So if it's unbiased, bias will be 0, definitely. Okay, it is good to have unbiasedness for an estimator, but that's not the only measure for the closeness because we also want to control the variation, the spread around the center. So we typically introduce the concept called minimum variance unbiased estimator. So what it tells us is that it is better to have the distribution of estimator, which is less spread around the true value. For example, if there are two estimators, and if their distribution have this type of spread, for example, here is distribution of theta 1 hat, and here is distribution of theta 2 hat. The reason, by the way, the reason that this estimator has a distribution is that the realization of these estimators, the realization to a specific value, for example, the sample proportion, is randomly determined by which random sample we are obtaining from the telescope, for example. So for example, here, if the unknown true value theta is 0, as the figure indicates, some possible realization of, let's think of some possible realizations of theta 1 hat and theta 2 hat. So possible realizations can be pretty different. For example, theta 1 hat, the possible realization, I mean, this is arbitrarily, possible realization can be 0.1, 0.2, negative 0.1, negative 0.3, etc., etc., etc. And the possible realization of theta 2 can be 0.1, 2, minus 1.5, minus 1, etc. Can you see the spread? The possibly spread of, I mean, the difference between the adjacent values. So in this case, we can say the possible values. Possible values, in other words, possible realizations of random variables, I mean the estimator. Realizations of theta 1 hat is, I mean, very less around theta, basically, because it has higher peak than the distribution of theta 2 hat. So it's less there, I mean, varying less around theta than those of theta 2 hat. In other words, I mean, the possible values, realization of theta 1 hat are more often closer to theta than those of theta 2 hat, because the distribution of theta 1 hat is more concentrating on the parameter value than the spread, than the distribution of theta 2 hat. So more often the realizations of theta 1 hat will be closer to the true parameter values. So if there are two estimators, both unbiased, then definitely we prefer the one with smaller variance, smaller spread around the true value. Mean square error is a composite measure of bias and variance. So this is the ultimate measure that we are going to use to judge the estimator. So mean square error, which is abbreviated as MSE, mean square error is basically bias squared plus variance. So if we think of, I mean, darting, then we know that it is better to be centered around the center of the, I mean, the bullet point, and it is better to have less spread around that eye of the ball. So it will be in this direction. The mean square error decreases, and mean square error decreases if the variance decreases as well. So this is the measure we are going to use to judge every estimator, because it's essentially what we want from the estimator is that the estimator is centered around the unknown true value with less spread around the true value. Before we move on to maximum likely estimation, let me try to answer a question. How can we link this back to our explaining data set? Can we have an astronomy example to help cement these concepts? I'm not sure which part you're talking about. How can we link back? You mean I think you're talking about the criteria. So let's say, okay, here. So in the example, in the exoplanet example, I use sample proportion. So we can think of that sample proportion as theta 1 hat. And let me use another estimator to infer the true population proportion. So what can we use in that case? What about the median? I know it's not quite sensible, but median is a function of the data, definitely. So let me say that is theta 2. So if you use median as a second estimator, it'll be 1 or 0 in the end, right? Because the 50th quantile of the whole observation will be either 0 or 1. So it's not very good estimator. We know that. So if we use 2 estimators, then definitely we can judge how good these 2 estimators are. So the reason sample proportion is great is that if we have more and more data, the distribution will be getting more and more concentrated on the true value. So we will judge those things, and we will learn in this lecture that sample proportion is superior to any other estimators when it comes to estimating some parameters in some circumstances. We will learn that. So in the exoplanet example, we can think of using different estimator to infer the true proportion of the Earth-like exoplanets. Okay, I think that's the answer. If it is not satisfactory, please come back to me. I answered James Nugas and Aaron. By the way, Aaron's question was from probability. So let me move on. So maximum likely estimation. Finally, we got to the main theme of this lecture. So this lecture is basically all about likelihood function, point estimation, where likelihood function will play the key role in point estimation, interval estimation, hypothesis testing, and the model comparison. So everything will be based on the likelihood function. So please pay your utmost attention to this part, because if you don't understand likelihood function well, then you are basically missing all the following contents. Okay, likelihood function of a model of the data, which is this is the basically probability distribution we are assuming on the data generation, is a joint probability density function or joint probability mass function of the observed data. And the most important thing is that we are treating this density function as a function of theta with fixed data. With fixed theta. For example, if the random variables that we are assuming for the n data points are continuous random variables, the likelihood function is basically the same as joint PDF, the probability density function of the observed data. And if I just specify that simplified notation, it'll be f of x1, x2, blah, 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 xn, given the model and the parameters. And if it is independent, if the data acquisition process is independent for each data, then we can say this joint probability density is a product of all individual probability densities. So many people ask me questions about the notation here. So this notation will be a multiplication version of, multiplication analog of summation notation, the sigma. For example, this is this represent a product of f of x1 given theta, f of x2 given theta, to the f of xn given theta. So this is basically a multiplication analog of summation, the sigma notation, product version of summation, summing notation, basically. So the most important thing here is to understand the likelihood function on the discrete cases. So if we assume the data are basically, for example, Poisson counts, which are definitely discrete random variables, then the likelihood function of the parameter will be the probability of observing the current data on your hands given the theta. And we will treat this theta as variable that can be changed in this function. Variable. Now, I'm not talking about random variable. This is just variable. And x is fixed. The same thing for the continuous case, although I forgot to mention it. It'll be fixed. And the entire likelihood function will treat this joint density function as a function of theta. This is a main variable in this function, in the likelihood function. So in a discrete case, likelihood function is a probability of observing the current data on hand given the theta. And we treat this joint probability function of observing the data as a function of theta. So everything is fixed except theta in the likelihood function. Also, if the data are independent, we can express the joint probability math function as a product of individual probability math functions. Okay, let me first explain the concept, and then let me answer those questions. So let's focus on the discrete case. In the discrete case, as I said, the likelihood function is a probability that we observe the current data under a model with parameter theta. For example, let's say the likelihood function evaluated at point A is way higher than the likelihood function evaluated at point 2. I'm talking about this example. It means that the probability of observing the current data is much higher. I mean, the probability of obtaining your data is much higher when theta is point A. Meaning that the data are actually telling us that I like theta equal to point A much more than theta equal to point 2. So you can think of a likelihood function as a tool to make the data speak more about which values of parameters are likely, which values of parameter are what the data telling us. So this is the fundamental idea, because our goal is to extract the useful information from the data, and the likelihood is a bridge of that process, a bridge between you and the data, because likelihood will be representative, saying which one is more likely value from the data. So that's why likelihood function is so important in statistical inference for both frequentist and Bayesian case. So here is an example of the exoplanet case. So we are interested in the population proportion of Earth-like exoplanets, and we are modeling the data using the Bernoulli distribution, which is our statistical model. And theta, the parameter of this Bernoulli distribution, will represent the true quantity, the true quantity of interest. In this case, the population proportion of Earth-like exoplanets. So this is our statistical model. Either this model is, I'm sure, 100% wrong, but it'll be helpful to understand which kind of uncertainty is involved in estimating those true proportion of Earth-like exoplanets. It'll be helpful for understanding the uncertainty structure of the problem, but definitely I'm 100% sure that this is not the true model that our gods generated the data. I mean, our God used to generate these data. So probability mass function of the Bernoulli theta distribution is theta to the xi times 1 minus theta to the 1 minus xi. And xi's are always binary, 1 or 0. Okay, based on the definition of likelihood function of theta should be the probability of observing the current data viewed as a function of theta. So it'll be probability that capital X equal to small x. And since the data are random sample, meaning that they're obtaining each datum doesn't affect the acquisition of the other value of the datum. So we can assume the independence here. So we can express the joint probability distribution as a product of individual probability math functions. And as I told you, the probability math function is theta to the xi times 1 minus theta to the 1 minus xi. So if we multiply these, n of them, then we will definitely have theta to the sum of xi, because the product becomes the summation in the power. And we learned, I know that this is unlikely, but I assume that the observed data says 40 out of 100 were Earth-like exoplanets. Definitely unrealistic, but for example, for example, with an easier visualization, I just said the data is 40. Sum of xi's are 40, because sum of xi's are sum of 1 and 0s indicators. And it turns out that 40 out of 100 were Earth-like exoplanets. So final functional form of the likely function is theta to the 40 times 1 minus theta to the 60. This is a likely function. If you visualize this function, this single number, a function of single parameter, you will see this beautiful Gaussian-like curve here. And we will talk about more about how we obtain the point estimator from this likely function. But the idea is we can, as long as we have some assumptions of the data, like the probability assumption of the data, we can actually get the likely function, and we can actually draw or visualize, if it is simple, the likely function. And maximum likely estimator is what we need to know from this 2 hours and 20-minute lecture. So maximum likely estimator is essentially a value that maximizes the likely function, as its name indicates. So in practice, when it comes to maximization, because obtaining maximum likely estimator involves the optimization, maximization. So when it comes to maximization, we typically maximize the likely function on a log scale, natural log. I'm sure you're familiar with log of base 10, but in statistics, mostly when you say log, it is natural log. So in this lecture now, I will typically use ln to distinguish that as a logarithm with base 10. So the reason we are using log likely function instead of likely function itself is threefold. So there are 3 reasons. First, likely function involves some multiplication. As you have seen, by definition, you have seen some product of some probabilities, individual probabilities. So if you multiply small numbers between 0 and 1 multiple times, the resulting value will be very small. So, numerically, it is better to work on the log scale to transform the product to summation, which is numerically stable. And that was actually the 3rd reason. And the first reason is that basically summation is easier than the product when it comes to optimization. So we try to transform the product into summation to find the optimizing value, maximizing value. And second, log function. Log function is strictly increasing function. It's like strictly increasing function, meaning that the maximizing value of the likely function is preserved as a maximizing value of the log of the likely function. And the 3rd reason is numerical stability, which I mentioned. The reason we need to depend on some optimized numerical methods is that not always we obtain the closed form maximum likely estimators. Sometimes the equation that we got to solve is not solvable. So we try to use some numerical method to find the maximum likely estimator. So in the previous example, we obtained the likely function, which was theta to the 40 times 1 minus theta to the 60. If you take log, it will be 40 times ln of theta plus 60 times ln of 1 minus theta. So as you can see, both functions are maximized at the same value, 0.4. So 0.4 is the maximum likely estimate by definition. And 0.4, the interpretation of 0.4, maximum likely estimation, is that 0.4 is the most likely value of theta that might have generated the observed data, because it maximizes the probability of observing the current data, which is probability of observing the current data as a function of theta. So this probability is maximized when theta is equal to 0.4. That's the interpretation of MLE. And let me check questions. I think our TAs and other panelists are answering quite well, so I appreciate them. I will get back to those questions after each class and review the answers as well. Another example, because in this short lecture note, this part has the most examples, because understanding likelihood in the beginning will be the key to the following contents. I really appreciate if you spend some time on understanding likely function. If you cannot understand it on the spot right now, because at least we have half of the contents tomorrow, so we have some time between that. So please make sure that you understand the likely function completely. That's the key to this statistical inference class. Another example, let's model the length of cosmic ray path using the exponential distribution. Oh, there is a question. So the plot on the strictly increasing. So when it comes to strictly increasing, when I say strictly increasing, I meant that the log function is strictly increasing. So this is not, this is log function, log of theta, log of x. The horizontal axis x. So this is not the log of x, but log of likely function, some concave function on the left panel. If you take log, it will be also concave. So it's definitely not strictly, the strictly increasing, I meant the log function itself, mathematically log function. If you are really after the parameter, doesn't it make more sense to maximize probability of parameter given data rather than probability of data given parameter, which is a question by Bib Ratip. And that's also a valid question, very historical question between frequencies and Bayesian. So if you believe that it makes more sense to put the parameter in the argument, if you think it makes more sense to put the parameter first and given the data, definitely you need to think of a way to turn this likelihood inference to a Bayesian inference. I'm not saying you're wrong. That's definitely historically very popular discussion, whether parameter goes first given the data or data goes first given the parameter. How do you know that you have chosen the right distribution for deriving MLE? So that's also really very good question from Tommy Slav. So that's definitely another question. So when it comes to the likely function here in this lecture note, assume that we didn't check the validity of the distributional assumption. So that is essentially a topic of model validation. So model validation is kind of, you're interested in the model given the data and the estimated parameter. So whether the model is reasonable or not. Your question is about model given the data and the estimated parameter. So there are many ways to check the model validation. In a regression setting, for example, it'll be the residual analysis, basically, called. For example, I mean, this is one of the many possible regions where you can validate the model. For example, in a regression model, you have the data and you have the least square estimators, for example, the slope and intercept, which is also MLE. And what you want to know is whether your linear model or regression model appropriately explains the data distribution. So we do residual analysis, but that's one step further than this class. Basically, what we will handle in this lecture will be about getting MLE given the data and model. So model is given in this class, but definitely your question is valid. Once we make an inference about the parameter, the next step is to check whether our model is reasonably assumed. So that's very reasonable question. That's also kind of two sides of coins. I mean, inference validation. So that's very valid question, but our class, let me emphasize, our class will focus on estimating parameters, and model validation will be the next class tomorrow. Jogesh will handle the model validation after inference class. So that's the answer to Tomislav. And Aaron's question, I think, from probability class, can you compare the likelihood of different? Definitely, yeah, we can definitely compare the likelihoods under different models, which I will cover at the end of this lecture under the topic model comparison. So that's very valid question. And even in the model comparison, likelihood will play the key role in determining which model the data prefers. Okay, that's the question to Andrew. Aaron's question, I think that's from probability. Powen's question, does the MLE method always give the same values of parameters as the best fit once found by posterior in Bayesian analysis? No. So if you, I mean, let me clarify. So we have about 400 people here, 336 people here. Some of them are familiar with Bayesian inference. Some of them are not familiar with Bayesian inference. So, but let me quickly answer your question, even though some people are left confused. So MLE, I mean, this is jargons that we will learn in the end. So please wait if you are not familiar with his question, Powen's question. So MLE will not always be the same as posterior inference because MLE is the most basically maximizing value of the likely function. Unless you are, unless in a Bayesian inference, unless you are using some improper flat prior that will make the Bayesian inference consistent to pre-consist inference, you will not get the same answer because your likelihood function will be incorporated with your prior information, leading to somewhat different posterior, leading to a posterior distribution that might be different from the likely function to the extent of the prior information you input. So definitely they are not always the same. And Kai's question, does log likelihood always have a singular maximum? Not always, but in most standard family distribution that you are assuming, it will be unimodal cases. But definitely there are pathological examples that you can find some flat regions in the likely function where basically the maximum likely function is in the interval, where the flat region is the maximized point. Definitely a good question, but in any likely function inference based on standard family distributions, in many cases you will not encounter such a multiple maximum likelihood estimates. Okay,
Tak, some people are asking whether you can post this hand with the annotated notes on the website.
Definitely, I would be very willing to share my
Okay.
slides. So my plan is this: just in case I cannot finish my lecture, basically 18-page long lecture note, then I will fill out the remaining parts with my detailed comments, and I will share it with everyone else so that they can follow up the part that I cannot cover in a limited time. But I carefully designed, so I will cover most of them.
Good.
So don't worry about that, and I will share the annotated notes as well. Okay, I answered everything, so let me move on. So the second example, I was talking about this example and I deviated. So the length of the cosmic ray path is modeled by exponential distribution, which has scale theta. So the data x is exponential random variable with scale theta, and its corresponding probability density function has this specific functional form. I just typed it because writing down this density function will waste my time. This is the probability density function of the model exponential distribution of the data. And to derive the maximum likely estimate of theta given the random sample of n cosmic ray path length, the n observed length given the data, we first need to derive the log likely function to get the maximum likely estimator. So to get the log likely function, definitely we need to derive likely function first. So likely function, as I said, is a joint probability density function of the observed data. But in this case, this is a random sample, meaning that the data are independent. So we can express the joint probability density function, I mean f of x given theta, as product of individual probability density functions. And individual probability density functions has this functional form. So we just multiply the probability density over indexes from 1 to n. So you will get in the end 1 over theta to the n times exponential function to the of negative sum of xi over theta, which is a likely function, but it is better to work on log scale for the three reasons that I mentioned. So we are taking log, natural log, ln. So we are taking ln, so we will get negative n times ln of theta minus sum of xi over theta. Just wanted to emphasize that this is ln because astronomers are familiar with log of base 10. And then we try, probably you have learned this in the calculus, a way to find the maximum, optimum value. So we take the first derivative with respect to theta on the log likely function, and we set that first derivative equal to 0. And then we try to solve the equation with respect to theta. So if we rearrange this equation, then you will get theta equal to sum of 1 over n times sum of xi, which is sample mean. And so our conclusion is that the MLE is a sample mean. Definitely, if you're careful about the calculus, then you might ask me a question whether it is maximal, because it can be minimal. So in standard family probability distribution, you will always get the negative second derivative. So it will be maximizing value. The maximum likely estimate, which is a realized value, will be the sample mean, small x bar. And the maximum likely estimator of theta will be the capitalized version, which is not yet realized. Once you have the data, then this capital X will be realized into a small x bar. The second example is over, and we are moving on to the third example of finding maximum likely estimate. So Van der in 1985 considered a luminosity function as consider that the luminosity function can be explained by Gaussian distribution pretty well. So the probability density function for the Gaussian distribution has this specific functional form. I just typed it because it is just waste of time if I just write it here. Here, mu is the mean visual absolute magnitude, and sigma is the standard deviation of visual absolute magnitude. And to find the MLEs of these mu and sigma square, given the data or the given the observed data of size n, in order to find MLE, we need to derive the likelihood function first. That's the beginning of the maximum likelihood estimation. So likelihood function should be expressed as a product of individual probability density functions, because this is a random sample, meaning the independence between the data. So it will be just a product of n Gaussian probability densities. And we are working on a log scale. So we will take ln, and it will be negative n over 2 times ln of 2 pi sigma square minus sum of xi minus mu square over 2 times sigma square. I mean, I'm just taking ln, log of base, log natural log. And to find the point that jointly maximize the likelihood function in 2 dimensions, we take the partial derivative with respect to mu and sigma square. And each partial derivative will be set to 0 to find the joint point that jointly maximize this likelihood function. So we are trying to solve this equation using parameter with respect to parameters. So once you rearrange the first equation, you will get the MLA equal to sample mean. If you rearrange the second equation, you will see that the maximum likelihood estimator of sigma square will be 1 over n times sum of xi minus sample mean square. So these two are optimizing these two are maximizing the 2-dimensional log likelihood function in the parameter space. So this is the end of practice for defining the likelihood function and finding maximum likelihood estimators. Then, if you remember, the flow was this. I talked about the criteria to judge estimators, and I introduced maximum likelihood estimators. And now it's time to see why these maximum likelihood estimators are best with respect to the criteria I defined in the beginning. So for that purpose, we need to learn 2 more concepts. One is Fisher information. I know that this is abstract concept. This is typically denoted by capital I sub n of theta. What it does is measuring the amount of the information about theta in the data. I told you that likelihood is a bridge between you and the data, because likelihood will be representative, telling you that data prefers this value, for example. And Fisher information is about measuring how good this bridge is, how much information is actually coming from the data. It is kind of a single numerical summary of the amount of information about theta in data. So it has pretty complicated mathematical definitions. But what I want to tell you is that Fisher information is basically measuring the average curvature of the likelihood function at theta. Let me give you an example. So let's say there are 2 likelihood functions, depending on 2 different models. Let's say here is one likelihood function, and there is another likelihood function. Possible. So what I want to say here is that this is the first likelihood function. By the way, let's say they are centered at the MLE. I mean, by definition, because they are maximizing likely function, they should be MLE. It should be MLE. This is L1 of theta, meaning the first likely function. And let's say this is L2, the second likely function of theta. By the way, it doesn't look like the center. So let me try to draw it beautifully one more time, making it look like, oh, I'm bad in maybe this. Sense maximized at the MLE. Anyway, my assumption is that MLE is the same for both likely function. For the first likely function, it has a steeper curve at the MLE, right? Steeper curve at the MLE, meaning that it has more information about theta. On the other hand, the second likely function, it has a flatter curve at the MLE. I think my initial draw was more informative in this case, like this. Anyway, so it means that it has less information about theta. So Fisher information, mathematically complicated, but the key idea is it measures the amount of information about theta in the data. And basically that is a curvature of the likely function. And Kramer-Rouse lower bound. Kramer-Rouse lower bound, specifies that for any unbiased estimators, the variance of the estimator cannot be smaller than 1 over Fisher information. So what it says is an unbiased estimator achieving Kramer-Rouse lower bound, an unbiased estimator achieving this inequality, Kramer-Rouse lower bound, achieving this Kramer-Rouse lower bound is the MVUE, the minimum variance unbiased estimator. Because we know that achieving the Kramer-Rouse lower bound, it cannot get smaller variance than this estimator. Now it's time to see why maximum likely estimator is the best in terms of mean square error. So this is about symptotic optimality of maximum likely estimator. As n goes to infinity, as the data size increases, the maximum likelihood becomes an unbiased estimator with the most efficiency, the highest efficiency with the smallest variance achieving the Kramer-Rouse lower bound, and then it will be normally distributed estimator. So as the data size increases, the maximum likely estimator will have all three good properties. The wannabe properties, kind of. So it becomes unbiased. The center of the distribution of the MLE will be the true parameter value. And since this is unbiased estimator achieving the Kramer-Rouse lower bound, the variance equal to 1 over Fisher information will be the smallest possible variance out of all the estimators. And on top of that, in a symptotic case, this maximum likely estimator will be normally distributed. So it will also define the shape of the distribution as well. So in other words, if the data size is large, if the data size gets larger and larger, and in practice, if the data size is pretty large, then we can say that there is no other estimators more efficient than the maximum likely estimator. So for many cases, of course, this is not all cases, because the assumption of this optimality is that the data size is getting increased. is increasing basically, which is unrealistic. But if you have pretty many data points, then you can actually depend on this optimality property. So this is why the maximum likelihood estimator is the best from the criteria that we define in terms of mean square error. Because by achieving the Kramer-Rouse lower bound, we can say the criteria that we decide to use will be minimized. By the way, this asymptotic optimality maximum likelihood estimator has a good connection to probability theory, like central limit theorem, because the derivation of this property will be based on the central limit theorem. So that's why we call central limit theorem is so important in statistical inference as well. Because even though we don't use central limit theorem directly, most results in statistical inference were based already, were derived already based on the central limit theorem. So that's the maximum likelihood estimator. And definitely maximum likelihood estimators have limitations as well. The optimality is valid only when the data size is increasing, but in practice, we don't have such a luxurious setting where the data increases infinitely. So maximum likelihood estimator will be sometimes biased if the sample size is small. So be careful when your data size is small. And it doesn't give us all, it does not always give us a closed form solution. For example, as you can see, derivative, the first derivative equal to 0 and partial derivatives equal to 0. Those equations are not always solvable analytically. So we sometimes use the numerical optimizer to get the answer, the maximum likelihood estimators. So that's all about the point estimation. And let me handle some questions before I move. The second likelihood function is derived from a different sample or same sample. So I think Aditya's question is about this figure. So, I mean, same case. Let's say this is same data. Depending on the distributional assumptions you are making, you can have two different likelihood functions, right? Because likelihood function is a product of the probability distribution, probability density functions or mass functions that you define. So for the same data set, you can have two different shapes of likelihood functions depending on the distribution assumption, the statistical model that you're using. Of course, not all models are true, but some are useful. And it will be useful in a sense that if the likelihood will give us the most information that we can get from the data. So I think I answered the question, second likelihood. Okay, and then what is considered a small data size? So that's a very historical question because when I teach statistical inference, I always have the question, what is this data size enough to make a central limit theorem and relevant theories? Like, I mean, MLE theory, the optimality of MLE is based on central limit theorem. So the same limitation will be applied, same condition will be applied. So in an introductory level, undergraduate level statistical inference course, many books said if the data size is greater than 30, it is big, but I don't like that criteria. But definitely, there are many ways to see whether the data size is enough to use those optimality of MLE. In many cases, if the data size is large, you can simulate the data under the model that you assumed to see whether many simulations will produce the Gaussian-like distribution, some bell-shaped distributions. And I think in many cases, if your data have some bell-shaped distribution, even if it is a small size, if it shows some distribution like bell shape, I think that is a great justification to use the Gaussian assumption. Basically, Gaussian assumption related to optimality of MLE.
Sorry for interruption. Tak, it may be the right time to stop and take it from here tomorrow.
Okay, so let me double check the time.
2:45.
45. I'm sorry for spending 10 more minutes. I will continue tomorrow. And thank you very much. And I will follow up all the questions.
Okay, we'll meet again at 3 p.m. That is in another 5 minutes. Eric Fagelson will talk about astrostatistics, past, present, and future, and then it segues into introduction to R.